Hey guys, it's Steve again. Okay, we're ready for lesson 2 when it comes to memory in QB64. And before we talk about anything else, we want to talk about little Indians and big Indians. And I'm not talking about the Cherokees or the Apaches or any other Native American tribe. What I'm talking about is how the memory is stored. The values are stored in memory. Little Indian values are stored from right to left. Big Indian values are stored from left to right. And if you look at my screen, and hopefully I've changed the font and the resolution of the videos a bit so you can read it better now, I've wrote up a little bit of what we're going to be discussing. So what we're talking about here is, let's take the English language and we want to represent the value for the number 91. Well, if we write it down in English, we write 91 as a 9 followed by a 1. The 9 represents the 10's position and the 1 represents the 1's position. But what if we were writing in a language that wrote from right to left? Arabic runs from right to left. Hebrew runs from right to left. Well, I'm not an expert in those languages, and I've never actually used them myself, so I can't say for certain. But I'm assuming if we write the number 91 in Arabic or Hebrew, it'd be written as 1-9. The 9 still represents a 10 position, and the 1 represents the 1 position, but we're just writing them from right to left instead of writing the values from left to right. And that's basically the difference in little Indian values and big Indian values. Little Indian stores values from right to left. Big Indians store values from left to right. So this is important because when we're dealing with memory of any sort, we have to know how to read it. In most PNG images, they're written in big Indian values. Your red, green, blue, alpha is written in big Indian. Well, in QB64, we use little Indian. And I'll show you what that means here in an example or two. So, the first thing I'm going to do is dim me a variable, x. And I'm just going to call it as an integer type. And then I'm going to dim me another variable for a MEM type. And this time, I'm going to point my memory block to our first variable, x. You know, last time in the first demo, I made a new MEM block. It was blank, it had nothing in it. So, it was just whatever I wanted to put in it. Well, here, I want to look directly at the memory where x is stored. And that's what this little line here does. It says M is the memory block of variable x. And x is defined up here as an integer. So M is now a direct pointer to where x is located in memory. And to showcase this, I'm going to put a value in it. And if you look at this line, you'll see that I'm putting a value of 1, but I've specified what 1 is, because there's different representations of 1. As an integer, it's 2 bytes. As a byte, it's only 1 byte. As a long value, it's 4 bytes. So the program has to know how many bytes are we putting into this memory spot. So we're putting an integer, we're putting 2 bytes into memory. And we can see this simply by printing X. And there it is, a value of 1 on the screen. So X is equal to 1 now. Now, let's go ahead and reset X. We'll make it 0. I'm not going to put a 0 in it. I'm just going to use the standard X equals 0. Everybody knows what it does. So everybody knows this is reset X. And to prove it, we just print it. And there it is, 1 and then 0, which is what we've printed, and we've set the value for it. Now, let's put an unsigned byte into the first spot of X. Once again, it shows up as a 1. We've got 1 when we put an integer into X. We've got a 0 when we reset X with X equals 0. And then we've got a 1 where we put an unsigned byte into X. So, how does an unsigned byte hold the same value as an integer? Well, let's reset X, and once again I'll print it, but this time I'm going to print to the offset plus 1. I'm going to print into the second byte of our integer. And I'm going to print an unsigned byte. And now, we watch the value of X as we run the program. We start out, we put 1. Over here we put 1 into the value of X. So it's 1. Then we reset it and we get a value of 0. Then we put 1 as a byte into X. And that gives us a value of 1. Then we put a 0, we reset it, and we put a 1 the second time, well the third time now. We put a 1 into X this time, but we put it into the second byte. Well, the second byte gives us a value of 256. So, that's how our numbers are stored. Little Endian says the little values are stored on the left in memory, and bigger values are stored on the right. So the first position, the first byte, holds the values from 0 to 255. The second value holds multiples of 256 for an integer. So it's really important if you're accessing segments of your memory individually. If you're just looking for an integer, go to memory like we did at first. Put 1 as an integer in it, and it prints a 1 and a 0 both, and it formats it proper, and you don't have to worry with it. But if you want to work with the individual bytes of that integer, then you need to know that they're written in an opposite direction to what you would normally see. And where this really becomes important is because normally the value of white. Let's dim it first. Dim white. And I'm going to dim it as an unsigned long. This is to hold a 32-bit color value. So we dim white as an unsigned long. And we set it to full color values. So white is now all red, all green, all blue with full alpha. And let's print something to the screen in bright white. Hello world. Okay. Now I'm not going to run it just to show this, but we now know what'll happen. We'll print those values of X, and we'll print a hello world. But since we're using memory, and I'm trying to teach MEM through the tutorials, let's showcase a little bit of MEM here. So let's free the MEM first. And of course it's MEM free. Some of our commands are free, like free image. You have the free first and then the image. Well, MEM is MEM free, and I constantly find myself reversing those two values. So if you ever see something with me typing and it says free MEM, it's supposed to be a MEM free statement. So it'll error out and I'll have to correct it and go back to it, and that's what I just did. But let's free our memory, and now take our MEM and point it to an image. And here you can see I'm pointing it to MEM image 0. 0 is the display screen. It's what we're seeing, it's the visible screen. So in this case, now what I want to do is I want to do a loop, and I want to get some values from it. And what I want to get is I want to get an unsigned long, and I want to see if any of them are white. And if they are, I want to put a value of 0 where the red is. Well, actually this is where the blue is, and I'll get to this in a second. You would think it would be where the red is, but it's not, and I'll show you why. But right here, this is basically a little do loop. Get the memory from the screen. See, we've said the MEM image screen, so M is the screen. Get the memory from the screen, starting at the beginning of the memory, M.offset, plus O. Well, O is going to be my offset that I move from pixel to pixel. And down here I've got O equals O plus 4. Why is it plus 4? That's because on 32-bit screens, memory is stored in unsigned longs, 4 bytes per pixel. 1 byte for red, green, blue, and alpha. So we get our memory, and I'm getting an unsigned value. I'm comparing it against the white, and when we do, I'm putting a value here of 0 in the first byte, and the first byte is blue. It's contrary to your expectations, but I'll show you why, and I'll explain here in just a second. So, or maybe it's not. What did I do wrong? Okay, I see what I did wrong. What I did wrong is I put 0 as an unsigned long. I filled that whole color. I turned all my white transparent black. So we don't want that. We want to put an unsigned byte. If you can see where I made my change on this line here. And now with the sleep statement up here that I put in to debug, now you can see where we take the blue out. We have full red, we have full green. Red and green makes yellow. I just changed all the colors from bright white to yellow. Now, if I wanted to take all of the green out, I would simply add a +1. I'd move it over 1 byte. I'd change that byte to a 0. And here we have magenta, I guess is what it is, which is what you have when you have full red and full blue with no green. And if I want to take the red out, it's the next byte over. So, and we run it, and there you can see it in white. And now we got it in cyan, I suppose, which is full green and full blue. It's a green blue. And why it's stored like this is if we were to write our values in hex, white would represent 1, 2, 3, 4, 5, 6, 7, 8. 8 values of F. And what all these F's stand for, they're hex values. This stands for 256. And the next one stands for 256. And the last ones stand for 256. So, this statement, the and H says we're dealing with hex. This part here says it's a hex value. So, here where we're decomposing what it stands for, the and H is hex. Here, the first values are alpha. The next values are red. The next values are green and blue. So, this is how it's stored in memory. Alpha, red, green, blue. Now, we write it RGBA because most of the time alpha is something we don't worry with. We use the RGB commands, red, green, blue. And the A is tagged on for the few times when we need to actually change the alpha. But in memory, it's always stored alpha, red, green, blue. But this is the important part. QB64 stores this value in little Endian values. So we store it not from left to right, but from right to left, which means our values are going to be blue, green, red, and then alpha. And that's what we're seeing with above here where I'm changing my values. When I change the 0 byte, 0 is blue. So as I run this, I'm taking all the blue out. I'm setting a value of 0 for blue. And we have yellow, we have red, we have green, we have no blue. Red and green with no blue is yellow. So the 0 byte, because we start counting with memory at 0, the 0 byte is blue. Then the first byte, when we go to our offset +1, the first byte in memory is now green. So when I take all the green out of my white, that's where we get the magenta. So I hope everybody sees why it's important to realize that memory is stored in little Endian values inside QB64. We're storing the values right to left instead of left to right. So when we want an unsigned long, when we want the whole value, just get it as an unsigned long. Let QB64 deal with it alone. If I wanted to set my values here something in specific, I want to turn it to, well, let's just do it the easy way. Now, not everyone is going to have color 32 with their version of QB64 yet. I've pushed the changes into the repo. It's in the development build. So if you have the development build, you can have color 32. But here, I'm going to have a lot of typos. I'm going to push the value of gold into unsigned long. I don't remember what the color values of gold are, but there it is on the screen, gold colored text. I'm sending an unsigned long and putting it into memory. So all I have to do is give it the whole long value, and I don't have to worry about which byte I'm putting it in. Now, oddly enough, we can produce some strange results. And here I'm going to move my offset so I don't get an error, because I'm going to try to put 4 bytes at a time. So here I'm putting the color gold, but I'm shifting my gold values a couple of bytes over. So it's not gold at all. It's, well, light blue of some sort. So you have to be careful that you put your values where you want them to go in memory. The first byte of your screen starts at m.offset. That's what this is. The offset value tells us that's the first byte in memory. I'm adding the variable O to it every time I make this loop. And O increments by 4. Well, the increment by 4 in this case is because I know I'm working with a 32-bit screen. And 32-bit values hold color as red, green, blue, alpha. So you have the 4 bytes. So I need to increase mine by 4 bytes. Since I'm getting white and I'm putting gold back, everything's working just the way it should. And that's all there is to it. It's the main thing that you most of the time, you won't have to worry if you're dealing with little Indian or big Indian or big chiefs. But if you ever start breaking your values down into their segments, which is what we're doing here, we're taking the whole pixel. We're taking this whole pixel, which is white, and we're breaking that pixel down into individual bytes. We're breaking it down into segments. So when we do that, we have to know which byte is which and what represents what. So when you're dealing with a 32-bit image, you're dealing with the values stored in Little Indian, and that breaks down to blue, green, red, alpha values. And really, that's all it is to it. It's the same way that we were working with binary files. You get a value from memory, and you put a value in memory. MEM get, MEM put. It's not very complex, it's not very complicated, and when you're finished, you MEM free your block. And at this point, we're finished with this tutorial. So I thought I'd go ahead and share and let everybody see it and comment on it and see if they have any questions up to this point. And then I'll do another tutorial later and we'll get a little more in depth with some of the other things we can do with MEM. But for now, watch, ask questions, let me know if the screen looks better, if you can read the letters or if they still blur out, and how things do for you. And we'll go from here in the future. Have a good day, guys. Bye.